Yes, so we are looking at group points, and group points will link to what we call semigroups, and semigroup will give us a group. So it goes like this, it goes like this. These are algebraic structures, and by definition, algebraic structure is any non-empty non-empty set with either one or more binary operations. Which are defined in this non-empty group defined on it. So if you are talking about an algebraic structure, we are looking at an empty set Yes, so it has to be defined on it. So if we start with the group point, we are saying is group point must be it's an algebraic structure. So it's defined in a given non-empty set. So we need to have a pair of a given group. A given set which is non-empty. This G is an empty set which is grouped in is have at and defined binary operation star consisting. So this is a pair of these two. We are saying it's consisting of an non-empty set G, and we are saying it having binary operation star, okay, such that this is very key now. The non-empty set G is actually closed under the binary operation. So when you are talking about a group point, the key thing is that it shouldn't be being defined by a given operation in an empty set G, and if you define that, you'll find that the G will be closed. So this is actually a property we call closure property. So if you have an algebraic structure, which fulfills or satisfies a closure property, then that algebraic structure is what we call group point. It's group point. Okay, it's group point. Next, we look at semigroup. We see which kind of algebraic structure is this? We call semigroup. So this, by definition, the closure, it will mean that if we have n for G and G2 in G, okay, then G, define that, will be in G. So this is actually the definition of closure property. Remember, this is Dafika Academy. And if you want us to follow us, kindly don't forget to subscribe. So there is a subscribing button down there in our channel. Subscribe, share also with your friends so that they will be getting these ideas, whereas every time we post this kind of ideas, because they are very important to us for our revision. And if you have any question pertaining any field, either in applied mathematics or pure mathematics, you can just leave the topic down there and I will be glad to check on it. So let us look at semigroup now. When you are talking about semigroup, we are talking again in a given pair, because we are talking about an algebraic structure. We are talking about the pair G star, okay, which is the algebraic structure, and of course we have said G is an empty set. It's an empty set, and it's being defined and given operation star, binary operation star, and we say this algebraic structure is semigroup if this algebraic structure is closed and a star. That's number one. And number two, associative binaries, associative binary operation. It has associative binary operation. So this is what semigroup is telling us that semigroup is actually groupoid plus associativity property. So if it happens that, then that is actually a semigroup. That's a semigroup. It is a semigroup. So what we are saying here, we are saying for all G1, G2 in an empty set G, if we take G, actually we need also G3 here, so that if we take G1 star G2 star G3, okay, this will be same as G1, G2, G3, and this is the property that we call associativity property. This is what we call associativity property. This associativity property. And again, we know that by closure, G1 and G2 will be in G. So if this happens, then we know that this is associativity and binary closure property being satisfied, and that gives you what we are calling a semigroup. That becomes a semigroup. Okay, now let's look at examples of groupoid and semigroups. So we are saying a groupoid here will be, if we take this algebraic structure, it is clear that it is a groupoid. It's a groupoid because for all n m in the natural set, then n plus m will be in that set, which is now closure being defined. Another one is positive the integers. So those are groups. These are basically groups. And multiplication also. And multiplication. And division. And division. Then this one under division. That's a group point. But if we take natural numbers and division, this becomes this not obvious. This is not a group point because closure property don't hold. So that's true. Do not hold. On the other side, semigroups, example of semigroups, we can see that that's natural. Yes, natural and addition. Okay, and addition. If we take a group of matrices and real and either operations maybe and either in division or in addition, this one, they will also be a semigroup. But we know that as just what we have said here, if anything is not a subgroup, automatically it's qualifies to be a non-semigroup. So it will mean if a non-semigroup here, semigroup example here will be actually this one and a division. So this will be a non-semigroup because it's obvious that the associativity nature, the closure nature is not owned. Since closure property don't hold. Okay. Don't. So that's very true. And note that we have looked at two things: the definition of group point, and we have looked at definition of semigroup. We have looked at the definition of semigroup. We have seen both of these are algebraic structures. We have seen the algebraic structures. The algebraic structures, and the properties that define them is very simple. It's the closure property and associativity property. If it's closure alone, that becomes a group point. And if it's closure and associativity together, this now become a semigroup. And we have given some example on this. To this point, kindly subscribe, and you share with your friends, and you leave any comment on this matter, and we will be looking at them as we proceed. Until next time, that's good, and thank you for your time.